All right, today's video is about net ionic equations. So basically what we've done so far is we have written equations and we've balanced them, but now we're going to talk about the idea of what's called a net ionic equation. A net ionic equation is just a way of writing a chemical equation where you're only showing the things that are changed from one side to the other. Okay, the things that are changed stay in the equation. The things that stay the same from one side to the other, you remove, and those are referred to as spectator ions. So in but in most net ionic equation, you're going to have some things that are changed, and those stay in the equation, and you have other things that stay the same, and again, those are called spectators. Okay. In order to do this, though, we have to use the solubility rules we just learned about strong electrolytes, non-electrolytes, and weak electrolytes, okay? If something is a strong electrolyte, which you already know what that is by now, then you have to break it apart. If it's in water, and most of these reactions will occur in water, then you have to break those strong acids and those alkali metals, ammoniums, and nitrates apart. If it's a non-electrolyte, then you don't break it apart. And if it's a weak electrolyte, you also do not break it apart. The only things you break apart are these strong electrolytes. Okay, so easiest way to do this, and one more thing. If you produce a solid, so if you produce something on the product side that is insoluble, and remember the non-electrolytes are those insoluble ionic compounds, that solid that's formed is called a precipitate. Okay, and that type of reaction is called a precipitation reaction. If something precipitates, it means that you have formed a solid. Okay, the solid is the precipitate. So if you make a solid, an insoluble ionic compound, in a reaction that's a net ionic, it's a precipitation reaction. So when we do this, we're just going to write the reaction. And again, this is a good way to start. A lot of times these are what we refer to as double replacement reactions. Because now instead of thinking about what's the equation, now we're thinking more of what's happening in the water. You have a solution of manganese nitrate, okay? So you've got a beaker here that's got filled with water, and you put some manganese nitrate in there. Well, do you really have manganese nitrate in there? No, you don't. What you really have is you have a bunch of manganese ions and a bunch of nitrate ions floating around in there. And why is that? Well, because it's got a nitrate in it, and all nitrates are soluble. And then you're going to pour in, basically, here's our other solution here. I'll make it smaller just so we can fit it. Another solution that has potassium phosphate in it. But again, is that solution really potassium phosphate? No, it's not. It's really a bunch of potassium ions and a bunch of phosphate ions. Okay? And then when you pour them together, so this we're going to pour into here. Now what we really have is a bunch of potassium ions, a bunch of phosphate ions floating around in there. And they're hitting each other, and they're bouncing off of each other, and they're attracted to each other, and they repel each other, and they're moving around all the time. And they can form bonds if they can. Okay, well, what do you mean by that? Okay, so let me erase this part here so I can keep going. Okay, so when this reaction happens, again, there's lots of different ways that things can combine. Okay, the manganese could hit the potassium, the manganese could hit the nitrate, and the manganese could hit the phosphate. Okay, first of all, two metals hitting each other, they're both positive charges, nothing's going to happen there. Okay, the manganese hits the nitrate though, and that's what we started with though, and that is soluble. They're not gonna stick together. Okay, but the manganese could hit the phosphate. And do we have a solubility rule about phosphate? No, we do not. Okay, so typically what you do to start this is you go, this is a double replacement reaction where the potassium and the manganese are gonna trade places. Okay, so we get KNO3 as one product, and MnNO3, no, not NO3, sorry. Mn, and it's plus 3, and phosphate's minus 3, so you get MnPO4. Okay, so we just write the regular normal equation, okay, which you can see it right here. Okay, that's your first step. And again, as you get more comfortable with this, you can kind of skip some steps. Okay, our next step is now we want to balance it. Okay, so the 1 manganese, 3 nitrates, 1 nitrate. So I put a 3 there. Okay, 3 potassiums, 1 phosphate, it's balanced. Okay, so after it's balanced, now we have to start thinking about, is it really like we just drew in that picture there, when you have this solution of, again, a bunch of manganese ions, a bunch of phosphates, a bunch of potassiums, and a bunch of nitrates. Okay, as they're hitting each other and bouncing off of each other and attracted to each other, okay, is manganese nitrate, is it going to be MnNO3? No, it's not. So we need to break that into ions. So Mn, now how did I come up with 3 plus on that? Manganese is a transition metal. Nitrate has a -1 charge, and there's 3 of them. Okay, so that becomes manganese 3 plus. Now, because there's 3 nitrates, watch how I write this. It's 3 NO3 minuses. Okay, because there's 3 outside the parentheses, so that comes back up to the front when you separate them. So for every 1 MnNO3, there's 1 manganese ion and 3 nitrate ions. Okay, and then we do the same thing with the potassium. So we have K3PO4. Is that soluble? Yes, it is. So we're going to produce 3 potassium ions and 1 phosphate ion. Okay, and then on our product side, oops, yeah, I know you guys caught that. I forgot the 3 there. Okay, we have 3 potassium nitrates. Is that soluble? Sometimes when I see ones like that, I think, oh yeah, it's actually double soluble. Don't say that, but, oh, it's got an alkali metal and a nitrate in it. Yo, definitely soluble. So 3 K pluses and 3 NO3 minuses. And then what about manganese 3 phosphate? Is that soluble? We don't have a rule on it, so no, it is not. So we just have MnPO4. Now, this is just like the normal equation. You might call this the molecular equation. This is what you would call the ionic equation, where you separate things into ions. And then our last step is the net ionic. So the net ionic just says, okay, now go through and cancel things out that are unchanged from one side to the other. For example, I have 3 NO3 minuses. Here I have 3 NO3 minuses. They're gone. Here I have 3 potassium ions. Here I have 3 potassium ions. They're gone. So the net ionic equation is just the things that are changed from one side to the other. Okay, so that Mn3 plus PO4 3 minus, making MnPO4, is our net ionic equation. And again, why? Because every time a potassium hits any of these, what's it going to do? It's going to stay apart. It's soluble. Okay, it is not going to combine with anything in there. Okay, nitrate, the same thing. No matter what nitrate hits, it is not going to form a bond that's going to stay. Okay, the only thing that does is when this manganese hits one of these phosphates over here, then they're going to stay together. Okay, that attraction between them, the ionic bond between them, is strong enough to keep those ion dipole forces from pulling the MnPO4 apart. Okay, and that is a solid in our product there. Okay, and that is and you can see every single step here. Step 1, there's balancing it, there's the ions, and then again, you've got the precipitate. Okay, let's keep going here. Okay, C2C5COOH plus NaOH. Now here they wouldn't necessarily expect you to be able to go, oh, that's a double replacement reaction, even though it is. Basically, the sodium and that hydrogen right there are going to trade places. They wouldn't expect you to know that. So notice that the hydrogen gets kicked off. Notice there's no hydrogen on the end here, but then the sodium there is in the front. And then the H goes with the OH to make H2O. Okay, now it's already balanced. And so then our third step is, okay, split things apart that are soluble. Okay, that is a whole bunch of nonmetals, always insoluble. Sodium hydroxide, though, has an alkali metal in it, so we break the sodium and the hydroxide apart. And then sodium and whatever this is here, Doesn't matter what the rest of that is. If it has a sodium in it, you break it apart. Okay, and then obviously water does not split apart. Okay, and now we look here at our ionic. Remember, this is our ionic one here. And we go, oh, yep, sodium plus, sodium plus. What if one side's sodium and one side's sodium plus? Do they cancel? No, they do not. And that's why those charges are really, really important. Every time you break something apart, you're going to end up with a positive charge and a negative charge. Okay? So, let's look at example number 4 here. These are actually from pretty recent exams before and then we'll see how much time we have left. On 1 through 5 up here, maybe on example 3, I'll just write down the correct answers for you and you guys can check them. So, while investigating the chemical and physical properties of metallic element E, so again, a made-up element, a student conducts an experiment by combining E and HBr. And as soon as you see HBr, you go, soluble, because that's one of my 7 strong acids, and that's really, really important. Okay? So, and we know nothing else about E, other than it's a metal. Okay? They combine E and HBr, which react according to the following equation. Write the net ionic equation for the reaction. Okay, so they've written the equation. They've even balanced the equation. So now we're just to the part where we have to break things apart if they are soluble. Okay, so we're going to go E plus. We know that HBr is soluble, so we're going to break that into 2 H pluses and 2 Br minuses. And that is going to make EBr2. Now, do we know if EBr2 is soluble or not? It says metallic, but that's all they tell us. Okay, just because something combines with this, and notice here that there's 2 bromines, and if there's 2 bromines, because what if it was just EBr? And that would be a little bit tricky, because if that's true, then it's very possible that E could come from that first column. Okay, but we don't even know that. It could be like copper, right? Copper could form CuBr. So there's not enough information here to determine, is EBr2 soluble or is it not? Okay, so therefore, if you don't know if E is a soluble alkali metal, which it definitely is not. It's EBr2, so it's definitely not an alkali metal. And it's not ammonium, because that's +1. Okay, and obviously it's not nitrate. Nitrate's negative. So this has to be something that has a +2 charge. And if it has a +2 charge, then it's not one of our solubility rules that we've learned. So what do? We leave that together like that. Okay, and now we cancel things that are the same on both sides. Is anything the same on both sides? No, it is not. Okay, it has to be the same charge. Everything has to be exactly the same. So what's the net ionic equation? That's the net ionic equation right there. Okay, sometimes nothing cancels. Okay, a student observes a piece of metallic nickel in a solution of silver nitrate. Observes the reaction. Okay, write the balanced net ionic equation. So again, they've written the equation. They've balanced the equation. Now we just need to separate things. And again, don't worry about the solid liquids and stuff like that. Okay, so Ni plus silver nitrate dissociates. Why? Because it's got a nitrate in it. So remember, you break that into 2. So 2 Ag pluses and 2 NO3 minuses make 2 Ag plus, and then here, is this one soluble? Yep, because it's got a nitrate in it. Okay, and here's where some of that thinking has to come in. Nitrates -1, and there's 2 of them. So that means the nitrates all total are -2. That means that the nickel is +2. Okay, so Ni2 plus, and then 2 NO3 minuses. And then things that are the same on both sides are the nitrates. They're both gone. Okay, and then we write just the overall equation. Okay, and that is correct. And you should notice here, not much is happening here. Nickel goes from a 0 charge to a +2, and silver goes from +1 to 0. Really, all that's happening in this reaction is electrons are moving around. Okay, nickel is losing 2 electrons, silver's gaining those electrons, and that's really all that's happening there. And again, that part you don't even need to worry about. Okay, that is our net ionic equation there. Okay, if you're like, yeah, I think I got this, go ahead and stop now. I'm going to go ahead and do these top ones here. And again, if you're feeling this is a little bit confusing here, so I'm going to go ahead and do these. But if you're like, no, I think I got this, then go ahead and stop now. So on this one, K plus OH minus, so K plus OH minus, Al3 plus 3 NO3 minuses is going to make, oh, you know what? I didn't balance it. Dang it. Let's see, I should have stopped, huh? Let's start again here. So first thing you want to do is balance it. 1 potassium, 3 hydroxides. 3 hydroxides. Put a 3 there for the potassiums. 1 aluminum, 3 nitrates, 3 nitrates. Okay, good. So 3 K pluses plus 3 OH minuses plus Al3 plus. And again, I'm breaking these apart because alkali metal. Nitrate plus 3 nitrates makes, and then on this side, the product side, 3 K pluses and 3 NO3 minuses. And then aluminum hydroxide. Oh, no rule about aluminum or hydroxide, therefore it is insoluble. And now I just go through, and things that are the same on both sides are gone. The 3 potassiums are gone. The 3 nitrates are gone. So my net ionic equation would be 3 OH minuses plus Al3 plus makes AlOH3. Okay, number 2. Cu plus Rb plus OH minus. Rubidium is an alkali metal, so we break them apart. Makes, not plus, makes Rb plus, and then CuOH, no rule about that, so I have to leave that together. Okay, and then I cancel things that are the same on both sides. Remember, this rubidium here has a positive charge, this one here doesn't. You can't cancel those out. They have to be exactly the same. Okay, so what happens there? Nothing. We're done. That is our final answer. Okay, for number 3, we've got lithium by itself. Potassium chloride is soluble. So K plus and Cl minus, making potassium plus, and then lithium chloride also soluble because, again, alkali metal. And then the things that are the same on both sides, chlorine. So our net ionic equation is you've got L, it would be Li plus K plus, making K plus Li plus. Again, similar to that one we saw below where, and oh, of course I forgot the plus on there. Okay, you have to have that plus on there. Okay, I was just looking it over at the end, making sure they all were the same. And if they aren't, then you screwed up. So you got to make sure that you've got these are different and those are different. So you have to leave them in. Okay, number 4, sodium carbonate is definitely soluble. So you're going to get 2 Na pluses plus CO3 2 minus. Hydrochloric acid is one of your 7 strong acids. And again, I forgot to balance it. So we're going to back this up again. 2 NaCl's for the 2 sodiums, 2 HCl's, and I think now, yes, that is balanced. So 2 Na pluses plus CO3 2 minus plus 2 H pluses plus 2 Cl minuses make 2 Na pluses plus 2 Cl minuses plus H2O plus CO2. Okay, things that are the same on both sides. I see 2 sodiums, 2 chlorine ions, and that's it. So overall, we're going to have CO3 2 minus plus 2 H pluses, making H2O and CO2. And that is your correct net ionic equation. Okay, and then number 5, we've got 4 carbons, 5 H2Os, but now we have an odd even problem. So now we're going to go back and double everything. That's 8 CO2s, 10 H2Os, and that makes a 16 plus 10 is 26, 13 O2s. Okay, and it's all molecular compounds, so there's nothing that dissociates out of any of that. So that is not only the regular equation, it also happens to be the net ionic equation.